we're going to look at a couple more different indeterminate forms and how to deal with them for limits. So here we're looking at the limit as x approaches 0 from the right of 5x, that whole quantity, to the 2x. So this is the form 0 to the 0 power. 0 to the 0 power is indeterminate, so we need to find a way around that. We'll do the same thing that we did with indeterminate forms of 1 to the infinity and infinity to the 0, where we'll instead look at the natural log of 5x to the 2x. So we'll investigate the limit as x approaches 0 from the right of this function. And for natural log of 5x to the 2x power, we can pull the 2x out in the front. Now, we got to keep in mind as we're working through this that when we get to the end, when we find this limit, that's not our actual answer. Because in order to get back to 5x to the 2x, we have to exponentiate this. We have to raise it as an e to this power. So we'll have to take our result of this limit and do e to that power. So when we look at this limit, we end up with 0 times the natural log of 0 from the right, which is negative infinity. And this is another indeterminate form that we'll have to turn into either 0 over 0 or infinity over infinity. So we'll turn it into the limit as x approaches 0 from the right of natural log 5x over 1 over 2x. And now we're in the form of an infinity divided by another infinity. Once we're there, we can use L'Hopital's rule to take the derivative of both the numerator and the denominator. So the derivative of natural log of 5x is 1 over 5x times the derivative of 5x. And we'll divide that by the derivative of 1 over 2x, which, if you use the quotient or the reciprocal rule, comes out to be negative 2 over 2x squared. And this will give us a limit as x approaches 0 from the right of 1 over x over negative 2 over 2x squared is negative 2 over 4x squared, which is negative 1 over 2x squared. And if we flip that around to simplify it down, we'll end up with the limit as x approaches 0 from the right of negative 2x squared over x, or just the limit as x approaches 0 of negative 2x, which is 0. And now, since we got 0 for the limit of the natural log of our function, we will exponentiate our answer. The limit as x approaches 0 from the right of 5x to the power of 2x should be e to the 0, which is 1. For this next one, we've got a new indeterminate form. This one is infinity inside of this radical, because infinity squared plus infinity is infinite, and if you square root something that's infinite, it's still infinite, minus just infinity. Infinity minus infinity is another indeterminate form. And there's a few different ways to deal with this one, but if we're trying to get it into a way that we might use L'Hopital's rule, we needed it to be a fraction. And so to turn this into a fraction, we can multiply by the conjugate. So we'll look at the limit as x approaches infinity of x squared plus x minus x times the square root of x squared plus x, all divided by the square root of x squared plus x. And if we simplify out that numerator, the root x squared plus x times the root x squared plus x is just x squared plus x. The root x squared plus x times the x and the root x squared plus x times the negative x will cancel out, and we just have minus x times x, or minus x squared, left in the numerator, divided by, and we'll just leave the denominator the same for right now. We can simplify the numerator, obviously, into the limit as x approaches infinity of x over root x squared plus x. And if we try to use L'Hopital's rule on this, which we could because it's infinity divided by infinity, we're going to sort of come across a problem where we keep getting that same indeterminate form over and over and over again. And it's going to take quite a bit of work to get to a result using L'Hopital's rule. So we can also use a trick that we use with rational functions. The highest effective power within this entire the entire fraction is an x to the first power. So if we divide everything in the numerator and everything in the denominator by x, or in the case of the denominator, the square root of x squared, if we want to call it that, we should be able to come across an answer a little bit more easily. So we'll look at the limit as x approaches infinity of x over x over root x squared plus x over x squared. So we've introduced a square root of x squared into the denominator of this, plus x over x. So effectively we've multiplied both the top and the bottom by 1 over x. And simplifying that down gives us the limit as x approaches infinity of 1 over the square root of 1 plus 1 over x plus 1. And as x goes towards infinity, this becomes 1 over the square root of 1 plus 0, which is just 1, plus another 1, or 1/2. In this last one that we're going to look at, we've got 1 over 0, which is infinity, minus 1 over 0, which is another infinity. So again, we've got infinity minus infinity. And oftentimes what we want to do in this case is find ourselves a common denominator. So the common denominator between our two fractions will be x sine x. So we'll end up with x minus sine x if we multiply the first fraction by x over x and the second fraction by sine x over x, divided by x sine x. If we plug in 0, we've got 0 minus 0 over 0 times 0, which is 0 over 0, which means we can use L'Hopital's rule. If we take the derivative of the top, we get 1 minus cosine x over the derivative of x sine x is x times the derivative of sine cosine x plus sine times the derivative of x using the product rule. And the derivative of x is just 1. And then we'll plug in our 0. 1 minus cosine 0, well, that's 1 minus 1. That's 0 over 0 plus another 0. Okay? So we'll reapply L'Hopital's rule. We get the limit as x approaches 0 of, the 1 will go away this time. The derivative of negative cosine should be positive sine. And then the derivative of x cosine x will be x times the derivative of cosine, so negative sine x, plus cosine x times the derivative of x, which is just 1, plus the derivative of sine, which is cosine x. And now when we plug in 0, we've got 0 over 0 plus 1 plus 1. So this is 0 over 0 plus 1 plus 1, giving us 0.